have kind of a template here already built, kind of a skeleton for us to look at. And really, linear motion is exactly what it sounds like. It's things moving in a line. The way that this unit is going to kind of progress is we'll look at just things moving in a straight line, we'll look at them going at a constant speed or velocity, and then we'll look at them going at kind of constant acceleration, so speeding up or slowing down. And then we'll kind of level it up. And then we'll look at two-dimensional motion, where the velocity is maybe constant. And then we'll look at 2D motion, where then it's speeding up or slowing down. And that's when we'll kind of get into like cannonballs and bullets getting fired. And I might even go fire off a potato gun and kind of show a video of it. And we'll kind of use that as a way to kind of do some practice of these equations. And so for constant velocity, so really that means not speeding up or slowing down, no change in speed. And really that should, I guess, say velocity. Velocity has direction again, remember. And so far, we know that velocity is just the change in position, how far it's moved, or distance, divided by the change in time, okay? And you could kind of break that down if you want. You could kind of rewrite that more as like calculating slope in a math class, like, oh, x1 minus x2 over t1 minus t2, and we kind of know that. And so just to kind of save space and time and out of laziness, I'm not going to write it like that. But that's kind of how that works under the hood. And we also know that acceleration is the change in velocity over the change in time. And throwback to hopefully middle school, we also know that slope is just the change in rise over the change in run. So kind of knowing that, if I want to look at constant velocity, well, I would have here my x, that's my distance, that's in meters. My time, that's in seconds. We're not going to use inches or feet or miles. We'll use kilometers and meters and centimeters in our class. So that means velocity is then meters per second. Time is still seconds. And acceleration then would be this kind of weird one, because if acceleration is the change in velocity, but velocity is already meters per second, and then you're dividing it by time, well, we do meters per second divided by seconds. So I'll look at kind of meters per second per second. Some folks also write it just as meters over seconds squared. That's kind of a math thing. You can kind of combine those two together. That totally works. I will say, though, that this one maybe makes a little more intuitive sense, because really this first chunk, meters per second, that's velocity. It's how much the velocity changes in 1 second. So I personally like this first way a little more. So with that in mind, well, let's think about constant velocity. If it's going at a constant velocity, that means then that if I change maybe my rule lines, kind of the grid lines, for instance, and I had like some little person and they're kind of walking around, right? So they're walking, they're going over here, and they're going at some constant velocity v, let's say. Well, let's say in 1 second they make it here. That means 2 seconds they'd make it here. 3 seconds they'd make it here. They're going at a constant rate, because in 1 second they travel 2 squares. Another second they travel 2 more squares. Another they travel 2 more squares. So it's kind of going at this constant rate. So thinking of that, then what we would really have, and let's use blue. What I would have then is, well, some constant rate for my person. And that's kind of neat. I have this little ruler. And so let's move my ruler up a little bit right there. So we would kind of have some constant rate for it. Okay. And maybe I even go ahead and I make mine a little steeper, just so we can kind of have a nicer looking graph, something like that. All right. So if we look at this now, I have a change in x, and then there'd be some change in time. Well, change in x and change in time, well, that kind of seems reminiscent of velocity, right? So really the slope here will give me the velocity. And so if I took the slope, that's actually how I would get this next graph. So we will take the slope. That's kind of the idea there. So if I took the slope, I see that, hey, well, the slope is constant here. And so again, this is kind of hopefully a recap, a little bit of a refresh, but this is a concept we'll come back to over and over and over. So I'm going to repeat this a lot until hopefully it's really deeply internalized. Well, if the slope is constant over here on the left, well, that means that my velocity is just some constant value over here on the right, is kind of the whole idea behind it, okay? Now, if let's say I wanted to find the area at some time here, then, well, I could go ahead, I could actually find kind of my, let's make this a little bigger, there we go, Wumbo size. We could kind of go in, we could find, oh, well, let's say this whole area in here. And we know really just that area is length times width, correct? So well, I'd have length times width equals area. So I really would have velocity times time, because it's really just kind of this rectangle is the area. And I could have done time times velocity as well. But really, that would then be having me multiply meters per second multiplied by seconds. And again, I've given this example before. If I had like 5/2 and then I times that by 2, well, I would just get 5 because this 2 and that 2 would cancel. The weird thing with physics is units can do the same thing. So that tells me then that the seconds down here and the seconds here actually cancel out, and I would just get meters. So the area of this represents the meters. So if I waited until this was at 2 seconds, it would tell me how far my little dude has walked at this 2-second mark, okay? So how far though, that is my displacement. That's my distance. That's how far it's gone really, right? And so to go from this middle graph, my velocity time graph, over to a position distance displacement versus time graph, kind of where it is at, this would be just me needing to find the area. That's all I would really have to do, which is pretty sweet, all right? So with that in mind, I'm going to clean this up a little bit. Now, looking at my middle graph here, kind of my velocity time graph, well, we can see my car's velocity is not changing, right? The car's velocity isn't changing at all. So is it accelerating? Well, it's not speeding up, it's not slowing down, it's not even changing direction, apparently. So there is no acceleration here. And I can tell that just because it's not speeding up and it's not slowing down. So really, again, to go from this one to this one, I would take the slope. So really, looking at this, saying there's no change in velocity over whatever the change in time is, so we really just have a big old zero here. And so that's what gives me zero acceleration. So that tells me then really that my acceleration is just right down there, something like that. So again, we take the slope. Now, again, this one I can't go ahead and like take the area to go backwards in reverse here, but you will have to trust me on it, and I will show you in just a moment actually that to go from this way to this way, we do just need to find the area again. Okay, now let's get a little more real here. So let's look at constant acceleration. Now, I have the same three graphs. I have my displacement versus time, my velocity, and I even put a little x here for the velocity in just the x direction. And then I have the acceleration in the x direction. All right, now I do want to mention that my t's look a little funny. I used to write t's just like that, but now I don't. I will always kind of try and curve my t's like that so you don't mix them up with a plus sign. So this one is actually a letter, and this one is just a plus. So just please keep that in mind, kind of take note of that, all right? I'll actually kind of just take this, put it over here, so we just kind of remember that, hopefully. And, oh, no, now I didn't want to do that. Let's make it a little bit smaller, so it's just kind of hidden a little more, I guess. So there. So that's a plus, and that one is a letter. And that's kind of just the structure for me to help save you from some confusion. So let's think about if I had constant acceleration here. If I had constant acceleration, well, that means my car's going faster and faster every second. So that means that if the slope here really represents the velocity kind of over in this graph, well, if the velocity is increasing, like I'm peeling out from a stoplight or something, right? That means my slope should be getting steeper and steeper and steeper. So really, I would have something maybe kind of like this. All right, we can see that it's getting steeper and steeper. So, and that's really based on the idea that the slope is the velocity. So since the slope is getting steeper and steeper, I can see that this is something that's speeding up more and more and more. So I want to take a couple little notes over here on the right side, and I'm going to switch back to a lined piece of paper just for kind of your sanity's sake. So I would say that since velocity is the change in displacement over the change in time, aka the slope, all right, we can see the object is accelerating. We can tell the object is accelerating. Cool. Now, it's going to get a little fancier here. If it was actually increasing and increasing and increasing like this, I will tell you that it actually is part of a parabola. Now, you didn't have to jump to that. Maybe that's like a, whoa, where did that come from kind of thing. But I want to actually kind of connect this and hopefully make the math that you're probably doing or have done in a math class maybe a little more meaningful and have a little more purpose behind it, really. And so this actually is a parabola. It's a parabola. I can spell. Okay, and so I'll tell you that your math teacher would say, well, a parabola has the format of y equals 1/2 ax squared plus bx plus c. It's like a quadratic, really is kind of what that is, okay? So now here's the thing though, and this is where it's going to get a little weird and kind of maybe a little odd and confusing here. We have different kind of conflicting symbols. Like your math teacher uses x in this equation to mean whatever the heck is on the x-axis. But the weird thing for us is the thing on our x-axis is time, right? So these really should be t's, all right? And then the thing on our y-axis is the position or the displacement, so x. So I'm going to rewrite this kind of in physics version, all right? And I'm going to say that it's x because that's the thing that's on the y-axis equals 1/2 the acceleration. That's actually a is kind of an appropriate symbol there just by chance. But now our x is really time, so we have time squared plus, now we have the initial velocity times, again, our x thing here is time, and plus some constant. Now for us, luckily, the constant is actually wherever the heck the object originally started. So this is the initial displacement. That's what this little tiny zero down in the bottom means. It's like initial, where it originally was at, what it was to start. So this would be like the velocity to start. So now the neat thing here, though, is I'm going to kind of just break this down a little more mathy for you math folks. This actually would change the width of it. This would make it narrower or wider. So narrower or wider. That's kind of neat. That's kind of bizarre. It's just kind of how parabolas work in this equation. So this one would shift the graph left or right. So this one would move the graph left or right. And this last little chunk of term here, this just would move the graph up or down. So this shifts the graph up or down. Now, you don't have to memorize this. I probably won't even mention this again in all honesty. You don't need to worry about the traits and how this behaves. But I want to connect this to what you're doing or have done or will do in a math class. So it actually has a little more meaning to it, all right? This actually is one of our main equations that's on our AP Physics 1 equation sheet. And so I just wanted to kind of let that be known. All right. Now, of course, on the AP Physics equation sheet, they do and use a different format for it, just to kind of make things a little more frustrating, it seems. So these are kind of our big three equations that we use in our class. And I'm just going to go and paste them down here so you can kind of see. There they are. And so we can see that on the AP equation sheet, they just flipped the order of these terms. That's all they did. That's it. So just please do keep that in mind. I know that's personally frustrating to me as well, and I wish it wasn't like that. So there we go. And I do want to mention that, again, this X naught thing is really that initial position. And I will mention one more note. You kind of get to choose this. You can kind of set this at 0. So like if I don't know, I was walking along and I was actually started running, so I'm speeding up, I'm accelerating. It's some kind of graph like this then that's going on with me, right? Well, you could choose to say, well, Johnson's, let's just say where he started was 0 and kind of make life easier. And that's totally fine because you can kind of choose to set where it is. So we get to choose, we kind of get to set this. So you, not me, you get to choose this. And I'll tell you, most of the time you're going to want to set equal to 0 just to make life easier. So you have one less like math term to worry about, all right? So let's keep going now. Let's look over at how constant acceleration, that's what we're looking at now, something speeding up, how would that look on the velocity versus time graph? Well, we can see over here in our first graph that, well, it's like constantly getting steeper and steeper and steeper and steeper. So it's increasing, right? Now, I'll tell you on Earth, it's going to increase at the same rate. All right. So if it's increasing at the same rate, we're actually going to get something kind of like the very first graph we drew on this page. So we'll get something more or less like this. So we can see that just like how the slope is increasing and increasing, well, the slope is the velocity. We see that here, the velocity is literally going higher and higher and higher and higher. It's increasing, which is kind of neat. So these two graphs, in a sense, tell the same exact story. So I can look at the first one and I can see, oh, hey, it's speeding up. It's going farther every second. So it's going faster every second. And then I can look at this one and say, well, the velocity is increasing every second. It's obviously going faster every second. So that's kind of neat, right? So let's look at this one. This is just a straight line. So math terms, I would say then that it's just a y equals mx plus b sort of guy, right? That's just kind of how that behaves in math land. And we know really that in our kind of land, though, we're in physics land now, our y thing is the velocity, right? And I actually called it v in the x direction. So it was just moving horizontally. So the way we would rewrite this then is vx is equal to, now, what the heck is the slope of a velocity and time graph? We said this at the beginning. Well, a changing velocity over a changing time, well, that is acceleration, right? So if I looked at this and said that, like, oh, it goes up this much and then it goes over this much, well, the change in rise, the change in velocity, divided by the change in time, well, the slope here is the acceleration. And I hope this is something that you're starting to get comfortable with. This is something that hopefully we gotta kind of have deep down as like a strong foundation. So that means our slope, our m here, is the acceleration in the x direction. Now, our x thing on the graph is time. All right? It is just whatever the time is, okay? Plus, and now this is the neat one, if I started out at some value, like if I took this and actually shifted it up here, well, that means I started at some velocity that's not 0, right? So my y-intercept here would be whatever my initial velocity is. Well, initial velocity would just be velocity initially. That little naught thing means initial. So what I want to do here is show that this is one of our big three equations. they reformatted it on the AP Physics equation sheet over here, but it's the same exact thing, right? These are the same thing, and they have physical meaning. Now, this second one, well, doesn't this equation, and I'll put a little X here just to kind of make that connection a little better. This equation also matches with the first one right there, right? These are the same thing. They just chose to switch the order of these terms just for I don't know what reason. I'm not the AP equation master, or at least the one who writes it, okay? Now, we know that the slope of this is really the change in v, at least here in the x direction, over the change in time. That is our acceleration, which is kind of neat, right? Now, the last thing that I want to mention here is that area. The area of this one is 1/2 base times height, right? Now, in our case, that really is 1/2, right? Time, really, right? Time multiplied by velocity in the x. So if I wanted to write that in terms of units, really, the area here is 1/2 seconds times meters per second. And this should feel familiar. I'm doing this again intentionally. What we see here is that wonderfully the units cancel. Let's use orange, disgusting orange. And we just get 1/2 units, or 1/2 of some number that will have units of meters. So really, again, what that tells us here, let's use the pencil even, that's kind of neat. What that tells us here is that the area of this graph tells us how far the thing has gone. So it's actually, it works the same as up here. We again just take the area to go back to where the thing is at. It works the same. It doesn't matter if it's constant velocity or constant acceleration. These kind of physical quantities, velocity, displacement, acceleration, all work the same, no matter if it's speeding up or slowing down, or kind of how they behave. Now, this one, we're finally getting to something kind of new and interesting. Well, here we said the slope is some constant value, and the slope we said is the acceleration. So that tells me then that really all I would put right here would be some constant value for the acceleration. If it was steeper, it would be a bigger value. If it was closer to flat, it'd be a smaller value. I'll just kind of pick something in the middle. And let's use red. There we go. So let's look at this now. We have acceleration and time. And again, I said acceleration has units of like how much the velocity, so meters per second, is changing every second. So meters per second per second. And I've talked about the slope of this one a little bit. The slope of this is the jerk. That's not on the AP Physics 1 content curriculum. So I'm not even going to talk about the slope of that. You don't need to worry about that one. The one that I think is valuable to talk about, though, would maybe be the area. So if I wanted to stop at this time right here and say, well, what the heck does the area here represent? What does that signify? What does that tell me about the world around me? Really is what I'm trying to say. The area here, well, area we know is just length times width, but in our case, that really means that area is the acceleration here in the x direction times time. But really, that's saying that, and I think I don't want to run out of space here, that's really telling me that the area is equal to meters per second times seconds. Well, I have 2 seconds in the denominator on the left side, and I have 1 second that I'm multiplying by. So this one and this one would kind of kill each other off. Or maybe it would be the other second that's kind of above it. Maybe this one. They both are really in the denominator effectively. So what that just gives me in the end is just meters per second. So the area of this graph represents the velocity, right? That's all it really is. It represents the velocity at a given time. So the neat thing here is that the area of this represents the velocity. That's kind of my proof of what I wrote right here. Find the area to go backwards. So if we look at my green graph, I see that every single second, the velocity is increasing and increasing and increasing and increasing, right? Well, if we look at the lower graph, I see that every second, and let's say that I took this and I didn't want to know the time I didn't want to know the area this time. Let's say I originally wanted the area over it this time. Well, I would have a smaller area, right? I'd have just this smaller rectangle to the left. But if I waited until a later time, I would have a bigger area, and it's going to constantly increase. Because it's this rectangle, it's just kind of constantly increase at the same rate. There's going to be more and more area. And so these match, these tell the same story, since really I'm again kind of thinking of this almost as like almost like it's filling with water, but the water's pouring in this way, which is kind of a weird thing to think about. I'm thinking of it like this, like in 1 second, maybe it fills up that much. The next second, it fills up that much again, that much again, that much again. It's saying that the area is constantly increasing here at the same rate, just like how the velocity here is constantly increasing at the same rate. So again, these graphs tell the same story, which is kind of the neat thing about it. And so hopefully by me taking a little longer than I was originally planning and talking about this more, you can see how all three of these graphs tell the same exact story. Now, you maybe are wondering, what about this third equation? I can do a derivation for it. That one I need calculus to do. I will include the calculus video either later today or over the next couple of days, and I'll post it if you're just someone that's curious and wants to know where the heck it comes from. But I will just write that down here kind of as a little reiteration. It doesn't connect to this graph though, and it's that the square of the velocity at some later time is equal to the initial velocity's value squared plus twice the acceleration in kind of this x direction. I'm assuming everything's moving in the x. We could have written just little y's for everything instead, and that'd be for something moving up and down, times the change in the displacement. Really, this bottom thing is just delta x, right? That's kind of the same thing. But really, I just wanted to give you the full version that they have given you on the equation sheet, okay? So this one, I can't do a little derivation for, but that is really like our last main equation that you are given as a resource for the AP test. So with that, let me know if you have any comments or questions. You can email me or ask me when I next see you in class. Until then, thank you for getting these notes done.